I hope you'll enjoy doing these volume by cross-section problems. I think they can produce some very interesting volumes. My suggestion, read each problem a couple of times, check the boundaries. First you want to draw the base of your solid. So here, think of it like the floor of your room. And here we have a sideways parabola and a vertical line. So I think what's usually helpful for many students, and you might quickly get past this, but first let's make a two-dimensional picture just of the floor. So this parabola has y squared, and it's a negative y squared, so it's actually open to the left. So if you put 0 in for y, you will get 2 for x. So this is our sideways parabola. That would be the point 2, 0. And our other boundary at x equals 1 would be over here. So the region bounded between them will be the floor of our solid. So I'll draw this larger when I make the three-dimensional picture. And then what we're going to do is make cross sections, and we can read this here. Each cross section will be a square perpendicular to the x-axis. So I'm going to pick a Riemann rectangle that crosses the x-axis. So our cross sections are perpendicular to the x-axis. So the key idea you're getting out of that is that the width of that Riemann rectangle is a delta x. So in our integral, that will become a dx. So some problems you might have cross sections perpendicular to the y-axis, and then you would have dy in your integral. All right, so while I have this two-dimensional picture here, what's going to be important is that you need to be able to find the distance across the parabola. So could you find the coordinates of these two black points? And if we just decided that our integral is going to have dx from the delta x thickness, then the interesting thing in this problem is we're given a function where y is the independent variable, and we actually want to change it backwards so that x is the independent variable. So let me swap sides. I'll add the y squared to the left, and I'll subtract the x to move it to the right, and then we'll take the square roots, plural. So this point now, if we let x be our independent variable, if I choose a random x coordinate, then the y coordinate here would be the positive square root of 2 minus x. And on the other side of the parabola, this is the same x coordinate, but this is where we would have the negative square root. So the distance across, the distance between these 2 points would be 2 square root of 2 minus x, the distance from one side to the other. And that's going to become the side length of each of our squares. So now let's see how we can do making a three-dimensional diagram of this. Well, use as much space as you can here. And now our vertical axis will become our z-axis. So we're going to have our x-axis and our z-axis, and then we're going to drop the y-axis to be that 45-degree line. But we know that we still actually mean for this to be a right corner, a 90-degree angle. It's just that we're trying to use three-dimension perspective here. All right, so the parabola wrapped around the x-axis. So my parabola would be going like this. And at this point, the vertex of our parabola was at 2, 0. And then the floor went over to 1, 0. Went backwards here to 1. So our cross sections then, so let me highlight. This is going to be our base. And then we want to put cross sections that are squares. So way back here, our square would be as tall as, that would be our tallest square. And where I drew that Riemann rectangle in the previous problem, this square would be a little bit shorter. So the height has to match that base across. And over here, and I'm going to erase a couple of these squares here in a minute, but you can see that there's not just one square. We're drawing one square, but it really represents all of these squares as we build a volume on top of that base. All right, so I'm going to pause and erase a couple of those so I have some room to write. So now I'm back to just this one typical rectangle, and again, notice there's our delta x or dx thickness of this Riemann rectangle we started with on the floor. So that dx would be the thickness of this square, so it's not really a flat two-dimensional square, it's really a prism, so the delta x would be the height. But most of this we're concerned with is the area of the square. So let me remind you, we found out that this point was x positive square root of 2 minus x, and this point was x comma negative square root of 2 minus x. So the side length of that square, so for one square cross section, the side length would be twice the distance. So this is going to be the side length. So each square then, we would take the side and square it. So for one square cross section, so you need not write that on your paper, but that has to be your plan, because now all we need to do to add up all of those square cross sections is to have an integral that varies. So our integral simply has to take those squares from 1 over to 2. So we're ready to set up our integral. So our volume goes from 1 to 2. And now all we need to do for the area of the square is take that side length and square it. So if it were a semicircle, we would use 1/2 pi r squared. If it was a triangular cross section, we would use 1/2 base times height. So whatever formula we have here is always going to be something different, not necessarily circles. So here we're adding up squares. So this is just side squared as our geometric formula for the area of a square. How it becomes a volume, remember, is that the dx gives it a third-dimensional thickness. All right, so if we square this, and whatever you might choose to do here, you could bring the 4 out in front, but this is going to become a 4 times this radical. So whichever way you choose to do it, if you wish to distribute the 4, or if you wish to factor a 4 and put a 4 out here, either way is going to work just fine. And now we do our antiderivative. So we would have 8x minus, raise that exponent to 2 and divide by it, so that would be a 2. And then we're going from 1 to 2. So feel free if you prefer to go back and factor first to have a smaller value, but this is pretty simple arithmetic. So we'll put 2 in and we'll have 16 minus 2 times 4. And then we'll put 1 in and we'll have an 8 minus a 2. So it looks like we've got an 8 minus a 6. So our final volume is 2 cubic units. So we could certainly do that problem without a calculator. All right, let's try getting a diagram for number 2. And again, you might be able to go right to your 3-dimensional diagram, but it might help first if you just do a 2-dimensional XY graph of the floor or the base. So we want vertices at 0, 0, 1, 1, and 2, 0. So this triangle is going to be the base. I wanted to grab that yellow highlighter. This is going to be the base. Well, I do know the equations of these lines both have slopes of 1 or negative 1. We're going to do cross sections perpendicular to the x-axis. So I could make my Riemann rectangle on this side, or I could make my Riemann rectangle on this side. Do you notice the symmetry? So do you notice that if I just went from 0 over to 1, then every rectangle on the left side has a twin on the other side. So I could use either of these, and here's what I mean. This line has the formula y equals 1x plus 0, and this line would have a y-intercept up there at 2 and a slope of -1. So these two lines could easily tell us these 2 points. If I did this point right here, it's simpler though. Whatever the x-coordinate is, the y-coordinate would be equal to x. So the equation of that line, y equals x. So this point would be x comma x, and this point would be x comma 0. Let's try to get back to OneNote here. If I use the other side, it would work. If I picked a typical x on the other side, then my y-coordinate would just be -x plus 2. So you could use a Riemann rectangle on either side, but I think that going from 0 to 1 sounds easier than going from 1 to 2. So we're going to have to use the symmetry here because we've got 2 different edges for our base. So that might be a lot of talking for something that hopefully was a little bit obvious to you. So now let's make our y-axis dropped here and get the 3-dimensional view of this. So our triangular base was at 0, 0, 1, 1, and 2, 0. Perhaps I needed more space over here. So let's stretch this a little bit. 2, 0. So this, oops, kind of missed there. This is our base. And we've decided that we're going to use the symmetry idea here. So I'm going to just have my integral go from 0 to 1 and then double it. So each of these Riemann rectangles, which I drew in red before, now I have this in blue, each of these are going to be the cross sections. And our cross sections this time were going to be semicircles. So I'm going to build a semicircle on top of that cross section. And of course they would get larger until we got to the center here at 1. So the 2 points that we're interested in here, this point is x comma 0, and this point, because this line, remember this line is y equals 1x plus 0, the 45-degree line. So because we know the equation of that line, sorry, I didn't mean to erase that. Okay, I'm back to the page I wanted. So because we know the equation of this line is y equals x, then this point can be called x comma x. So the distance across is our diameter. So the diameter here goes from x to 0. So the radius of that semicircle would be 1/2 of x. So we know the formula for the area of a semicircle, of course, would be 1/2 of pi r squared. So for each of our cross sections, we know that we're going to let the radius be 1/2 of x. So our integral, and again remember that we have to do some symmetry here. So if we let these range from 0, wow, I keep erasing here, sorry. If I go from 0 to 1, that's only half of our triangles. Then the second half would go from 1 to 2, and it would be exactly the matching triangles. So here we're going to use symmetry. So our integral is going to go from 0 to 1, and our semicircles, so 1/2 pi r squared dx. So our radius here is 1/2 of x. So we've got some arithmetic to clean up here. So if and you can bring constants to the outside if you wish. So if we bring this 1/2 out here, it'll cancel with the 2. And then we would just have to do our 1/2 of x quantity squared. So you could skip right to this next step here. So this is going to give us a 1/4 of x squared dx, and you could bring the 1/4 out too, pi over 4, and now we would just have to do the antiderivative of x squared, so that would be 1/3 x cubed from 0 to 1, and the doubling was already in there. So now remember, we could make this arithmetic even simpler, bring the 1/3 out there, and then we would have just the x cubed from 1 to 0. So our volume here is going to turn out to be pi over 12 cubic units. All right, let's see if we can speed up the process here. Number 3, our region is bounded by y equals square root of x and y equals x, a 45-degree line. All right, so let's get our two-dimensional picture of this first. So square root of x and y equals x. So this region, thin region here, which I'll probably exaggerate in my next picture, is going to be the base, and we already have seen these before. 0, 0, and 1, 1 are our intersection points. And on top of that, we are going to build cross sections perpendicular to the x-axis, and they are going to be squares. So I'm going to pick cross sections going across this region. So our thickness again is going to be a delta x because it's perpendicular to the x-axis. All right, so let's see if I can do a three-dimensional version of this. So our y-axis and our x-axis and our z-axis. So our 45-degree line, I have to definitely tilt here to give this perspective. And then our square root of x graph. Let me maybe get this y-axis out of the way here a little bit. So here's our line y equals x. Here's our square root graph going this way. Y equals square root of x. So right in between, here's the base of our solid. And our typical cross sections are going to be cross perpendicular to the x-axis, so make them parallel to the y-axis. That's important for your perspective. And we're building squares. So the thickness of this square is a dx. And of course, if I drew that square over here, it would be a little bit shorter. So it doesn't matter where you choose to draw a typical rectangle. So now what we need to know is our square. The square goes from one of these graphs to the other. So let's think about it. On this y equals x line, this should be a straight line, y equals x. So if this has an x coordinate of x, then its y coordinate is also x. And this point over here has the same x coordinate, but its y coordinate comes from the function value, square root of x. So the side s of each square, so the side of each square goes from square root of x to x. So for the area of the square, we would have to square that side. So what are we going to do here for our squares? They're going to go from 0 over here to 1. So our integral has to take us from 0 over to 1. And we're doing squares again, so all we have to do is take the side of our square and square it. And the thickness is dx. So let's see if we can FOIL here. Square root of x squared. Our product, our outside-inside product, are going to give us, when we multiply these, x times square root of x. So we'll have 2 of those. However you want to write that, we'll write it with an exponent next. And then the negative x squared will become a positive x squared. So let's think about writing this as a power. So this is x to the first times x to the half. So how about if we write negative 2x to the 3/2? So that we can do our antiderivative in our next step. All right. All right, so our antiderivative of x would be raise the exponent to 2 and divide by it. On our next term, we're going to raise the exponent from 3/2 to 5/2. So we're going to multiply by 5/2, and we will come up with, did I say multiply by 5/2? We're going to divide by 5/2, so multiply by 2/5. Sorry, I said that backwards. And we're going to raise this exponent to 3 and divide by it. And we're happy to have 0 and 1 here for our arithmetic. We substitute 1 in using our fundamental theorem. So 1 to any power is still 1. And then, of course, the zeros we wouldn't need to do. So let's see what we come up with here if we do, what is our common denominator? Should we do 30s? 30ths, 15 over 30 minus 24 over 30 plus 10 over 30. So what does that look like? 1/30th of a cubic unit. So why is it so small? Well, isn't the base just a little sliver of space here? Remember what it looked like? It was just a very small base, so our squares would be really very short. All right, so let's press on and see if we can finish up. All right, so this time we need a circular base. Again, I'll start with 2 dimensions. You need not. You can go right to 3 dimensions if you feel capable of doing that. And we're doing cross sections that are perpendicular to the base that are equilateral triangles. So how come it doesn't say whether they should be perpendicular to the x-axis or the y-axis? Well, our circle has symmetry, so it doesn't matter. You could take your pick. So personally, I think we're most used to doing cross sections that use x as our variable, so I think I would stick with a delta x cross section. And what's going to be important here is to know the distance across again. So think of our circle. So the equation of this circle, x squared plus y squared equals 1. So if we write it, you've seen this before, if we write each part of the semicircle, each semicircle of the circle, y as a function of x, so we could say this point up here is in the positive quadrant, so its y coordinate would be the positive square root of 1 minus x, and this point down here, this point, has the same x coordinate, and it would be negative 1 minus in the radical. So we now know this distance across. This distance across would give us twice that radical. So that's going to become the base of our equilateral triangles. So we're going to build equilateral triangles that have this length as their side. So it might be helpful before we start, remember your geometry. For equilateral triangles, instead of using 1/2 base times height, if you have a good memory, you can do that all in one step with the 30, 60, 90 triangles, side squared over 4 square root of 3. You could also do it the long way with 30, 60, 90s and use 1/2 base times height. All right, so let's see if we can make our 3-dimensional picture here. So this time we want a circle, so I'm going to, because of the perspective, I'm going to make my circle look more like an ellipse. Let's see what we can do here. So remember, this is our x-axis, our y-axis, and our z-axis. And then we decided that we were going to do cross sections across the x-axis. And we just came up with these 2 points. Looks like that point's on my z-axis, so I'm just going to slide that over. It was just badly drawn. So remember that this blue point over here and this blue point are what we were just working on. So this was our positive radical 1 minus x squared. And this point was at our x comma negative square root of 1 minus x squared. So we're going to build an equilateral triangle, and we're going to build those all the way across. So this is what we had determined, that the side of our equilateral triangle was twice the distance to one side. So we doubled the distance across. So the area of the equilateral triangle, if I use our side squared over 4 square root of 3, just to do some preliminary work here. So I'm going to square this side length, so it would become 4 times this value. And then we could cancel those two 4's. So I simply put this side length in for S. So when I squared it, okay, so this is the area of one cross section. This is the area of each cross section. So now all we need to do is put that into our integral. So you could do that preliminary work to save you, as long as you keep this labeled, so as long as it's clear what you were doing here. So now our volume of our solid, here we could use the symmetry. Notice that we want to actually range across. We want our integral to go across, sweeping from -1 to +1. But could we use the symmetry of the circle again? Couldn't we definitely go from 0 to 1 and then double? Because every triangle on the positive side has a matching triangle somewhere on the negative side. So symmetry definitely gives us these easier limits of 0 and 1. All right, so we've already done our area formula. So we could put this in here. So this is each triangle. And then when we put our dx there in the integral, we're adding up all of them. So this square root of 3, I think I would bring to the outside right away in my next step. And then you're ready to do your antiderivative. So integrate. Keep this 2 radical 3 out in front. So 1 is the derivative of x. And here we raise the exponent to 3 and divide by it. And we evaluate from 0 to 1, nothing to it. That's going to give us a 1 minus a 1/3, and then a 0 minus a 0. So here we have a 2/3. So I think we'll come up with 4/3 radical 3. And we don't know the units, but we know they would be cubic units. And I think we made it.